Another piece of this geologic timescale carbon cycle is to look at these strange events that happened in the Earth's history called the Snowball Earth episodes, first proposed by Paul Hoffman and Dan Schrag from Harvard University, based on some geological evidences of glaciations coming all the way down into the tropics. So that's very unusual in terms of having to explain the processes by which this can happen. Obviously, oftentimes you find evidences, for example, millennial timescale oscillation evidences are plenty in the system, but we don't have a very solid accepted explanation for where this time scale comes from. We have seen this before from this Michigan Technological University, I think, Michigan Tech, looking at the paleogeographic extent of continental ice sheets and permanent sea ice cover over the last 800 million years. Thrown in are here some major extinction events as well. The big known Snowball Earth episodes here are in the Neoproterozoic, so the later Proterozoic, the early life coming to the end of it by about 540 million years ago, where we have Cambrian, so this is often referred to as pre-Cambrian. So here in the Cryogen and Ediacaran, you have the Sturtian and Marinovan snowball episodes, and there are lots of debates not only about how this could have been driven, what could have brought the freezing all the way down into low latitudes. Plus, it's called Snowball Earth and not Ice Earth or whatever, because if you covered the entire planet with ice, then all the biology would presumably die, because you need somehow to keep light to reach the photosynthesizers. So that's why it's often referred to as Snowball Earth, so that you have some slushy ocean in the deep tropics, then you can show that light can penetrate, photosynthesis can go on, and so on. Okay, coming to our story here of the geologic timescale carbon cycle, we have plenty of evidences of glaciation reaching down into the mid-latitudes, like let's say 60 south, 60 north, or several times, but these are the ones that have to be understood in terms of our carbon cycle. We are still talking about the same basic principles of CO2 exchange, aqueous carbon and carbonic acid being formed, which is going to be moved into bicarbonate and H+, which further goes into carbonate and H+. Then you have calcifiers, which are going to lock up the calcium carbonate, and there is a detail here that we haven't touched on yet. How much calcium carbonate makes it to the bottom depends on the balance between the so-called rain rate, the rate at which calcium carbonate is falling down, and dissolution. Remember that the temperatures get colder as you go deeper into the ocean, and CO2 tends to increase, so you have more acidic waters, cold waters, where dissolution is high. So the depth at which the rain rate and the dissolution rate are equal is called the lysocline, or the calcium compensation depth, and any molecule of calcium carbonate that goes beyond it is going to make it to the bottom, because there the dissolution rate is lower than the rain rate. So that depends on the depth itself, obviously. So in coastal waters you can get deposits, and you have contributions from various things like corals, mangroves, organic carbon. So this is why before we looked at the burial rates of calcium carbonate, which is the oxidized form of carbon, and the burial rate of organic carbon, which is the reduced form of carbon. And there is the balance of oxygen involved there as well, because if you keep burying organic carbon, which is produced by photosynthesis where an oxygen molecule was released, then that unrespired organic carbon is going to start building up oxygen in the atmosphere. So this cannot obviously go on for too long. So we have to look at all these balances on long time scales, which is very fascinating. So looking again at the oxygen story, which we have done several times already, the best evidence of origin of life is somewhere here at 3.85 billion years ago. Appearance of oxygen producing photosynthesis goes back to about 2.7, 2.8, or something like, let's say here, this is 2.5, 2.75, so let's say 2.7 billion years ago. And the rise in the concentrations in terms of atmospheric O2 compared to today's levels happens here at, let's say this is at 0.6 or so, okay? And then there have been oscillations over time, and we are at the current levels. And you can see that in terms of atmospheric O2 percentage, again expanded over the 600 million years ago, so starting in the Neoproterozoic into the Cambrian and forward. You can see that there have been first animal body plans, Cambrian explosion, separation of systemic and pulmonary circulation, first terrestrial vertebrates, extinction of megafauna, and so on. And here we are at 20%, the current level of oxygen in the atmosphere. So along the way we have to worry about biology, because biology at some point, when it learned photosynthesis, reducing carbon to form the reduced carbon carbohydrates and sugars requires that it get electrons from somewhere. Right now the plants have figured out how to split water to get the electrons. Before, there could have been roles played by iron, sulfur, and various other things. Nonetheless, when first organisms, photosynthesizers, figured out how to split water to get the electron for reducing carbon from CO2 to CH2O, would have been a revolutionary strategy, right? So that has to be kept in mind as well when we are talking about freezing the Earth over, because you have to reduce CO2 in many ways, and photosynthesizers are part of the story, as we already saw, not only in the ocean but also on land by the time you get to the time where vascular plant appeared, Silurian, Devonian, Ordovician, and so on here. Okay, so looking at then the relation between partial pressure of CO2 parts per million by volume, going back to about 200 million years, we were again very high during the Cretaceous hothouse, when the dinosaurs were running around. There were no ice in the Arctic. Antarctica wasn't glaciated. Mammoths, dinosaurs, everybody was wandering in the Arctic Circle, which was 15 degrees C warmer than present. Very different vegetation and so on. So the Burner model for atmospheric CO2 would put the CO2 very high here. So if you're thinking about photosynthesizers who had already evolved, then you have to see what would happen to them as CO2 begins to drop, right? Over time, various processes that occurred, calcium carbonate burial, organic carbon burial, all those good things are happening, and the CO2 keeps dropping, eventually reaching the current levels of 280 ppm and so on, before the Industrial Revolution. Along the way, the photosynthetic pathways also evolved to adjust to the CO2 levels. Most of the plants we have on Earth are so-called C3 plants, corresponds to the number of CO2 molecules involved in the photosynthetic pathway of converting inorganic carbon into reduced hydrocarbon. When the CO2 in the atmosphere drops below about 280, 300 ppm, or maybe less than 200 ppm, they are not able to have enough energy to do photosynthesis anymore. So a new pathway evolved called C4 plants, which are all the grasses, most of the grasses we have now. And they evolved several times during Earth history, but now there is an increased global C4 increase, which is potentially also related to the evolution of Himalayas, evolution of the monsoons, evolution of the grazers in East Africa, and so on and so forth. So these are putting together the evidences. What is the point? The point is that the change in CO2 over time and oxygen over time has happened over many time scales, but coming back to Snowball Earth episode, that happened between 600 and 700 million years ago. Obviously that's before vascular plants and large-scale photosynthesis on land, at least, right? Nonetheless, for the basic goals of the course, where we have to worry about where we are headed into the future in terms of carbon cycle and response of vegetation, we have to keep in mind that as the carbon dioxide is increasing, C3 grasses tend to get favored, and as temperature warms up and CO2 drops, there are C4 grasses favored. This could have huge implications, of course, for many of the C4 grasses which are cereals and other grains that we depend on. Okay, so what is the story with Snowball Earth episode then? I'm just trying to link the various biological CO2, O2 processes and come back to this idea of freezing the Earth extensively. So this is theoretical calculation, Buriko-Sellers type calculation, where you are looking at the ice line latitude. So to what extent would ice line come down to from the pole towards the equator? And the solar flux, which has varied over time. So we started at 0.7 and we are at the current level, and it will keep increasing into the future. And of course there is the other variable, which is the partial pressure of CO2 in the atmosphere. So this would say that if you take the ice albedo calculations, solar flux and so on, and the CO2 levels in the atmosphere, the current levels are kind of potentially capable of having ice cover all the way down to the equator. It would be unstable, but it is still possible. And how does that happen? Essentially, you can have a situation with the same solar flux and same PCO2, a complete ice-free Earth. Okay, you can have ice albedo feedback, which would drive the Earth to be completely ice-free. Remember, the ocean can store a lot of the heat, so you don't need to necessarily increase CO2. You can reduce albedo by retreating ice, which would absorb more energy, even with the same solar flux, and keep building till all the ice disappears, right? But if you get into an unstable situation like it happened in the Neoproterozoic, you can drive, especially if the solar flux was lower, as it was at that time, and CO2 was lower a lot, then you can bring the ice line down. And the idea is that once you hit a certain latitude, like 30-degree latitude in both hemispheres, then the runaway cooling can happen and you can reach the ice level all the way down to the equator. Okay, but here we are at the present, where we have some glaciers on Antarctica, Greenland, sea ice in the Arctic, land ice over Canada and so on, and that's somewhere here. So if you reduce solar flux or reduce CO2, you can presumably drive the solution all the way to be glaciated, kind of like the Day After Tomorrow movie, right? So in the models, what they do is essentially look at the land distribution in the past, 700 million years and 800 million years, for a couple of scenarios, and then look at the weathering rates. So we are back to carbon cycle now, looking at calcium carbonate, and so on. And depending on the ice extent, the weathering rates can be high on land, and depending on the distribution of continents 700 million years ago compared to 800 million years ago, you can have very high weathering rates, because if you're in the tropics where temperature is warmer, and that also could increase land-ocean contrast and give you more monsoon-like circulation and rainfall, you could drive lots of weathering. So you can see higher weathering rates in terms of 10 to the 4 mole per kilometer squared per year of drawdown. And you can look at the flood basalts and other evidences that are also involved because of the mass extinctions we mentioned. They can last for tens of millions of years, or millions of years out to 10 million years, which would emit a lot of carbon dioxide. And you can see that there is flood basalt here 700 million years ago. So there is continental configurations which could give you tremendous amount of weathering and cover the ice and less than 0 degrees centigrade temperature all across the latitudes. So it's a combination of weathering, drawdown of CO2, continental configuration, and these feedbacks between ice albedo and sunlight, and the lower solar flux at the time would give us potentially these Snowball Earth episodes. This is just the details of how the model calculations were done by Pierre Humbert. You can see the continental configurations 750 million years ago, and how the glaciation was built from high latitudes into lower latitudes, eventually covering everything, and how it came out of it. How it came out of it is essentially again related to the weathering rates. So under normal conditions, you would have weathering where you have a metamorphism and silicate rock formation at the bottom of the ocean and so on, whereas at the surface you have weathering of silicate rocks. So these reactions are approximately in balance on geologic time scales, whereas under Snowball Earth you have covered everything in ice. So weathering is basically turned off, not only because it's very cold, but also because you have covered up all the weatherable material with ice, which would make the silicate rock formation and metamorphism dominate, whereas CO2 drawdown is not happening because CO2 emission from volcanic activity would continue. So CO2 would build up in the atmosphere and would dissolve eventually the ice that has built all the way down into the deep tropics. So again, CO2 is a critical player here, and the evidences for this come from looking at continental configurations, which is done by dating plus the magnetic information. A continent that's at high latitudes would have very different magnetic direct line angles looking at the rocks. So you take a rock, you date it to see at what time the magnetic lines were frozen, and then you look at the angles of the magnetic lines to say at what latitude it was. So these evidences called cap carbonates come from Namibia, which was still in the low latitudes at the time. This is 700 million years ago. Cap carbonates are basically huge deposits of calcium carbonate on top of the glacial deposits. Glacial deposits include tillites, rocks brought over from somewhere, and things that don't belong at that place, ground up, mixed up rocks, and so on and so forth. And when you remove the ice cover, there is going to be rapid reactions happening in the ocean that's going to produce sea level changes that are going to change the lysocline depth, calcium carbonate depth, and lead to massive amounts of calcium carbonate deposition. So you can see there are two cap carbonate evidences which allow us to date the glacial deposits coming all the way down into the low latitudes. The other evidences come from what are called BIFs, or banded iron formation. So when the glaciation happens and the Earth is covered in snow and ice, oceans are covered, so the oxygen exchange is blocked off, so ocean gets anoxic and the iron becomes soluble. But as soon as the ice disappears and oxygen begins to invade the ocean, then the iron in the ocean rapidly gets oxidized, so Fe2 plus to Fe3 plus, basically rusting, and that is insoluble, so it begins to get deposited in large bands. That's what it's called, banded iron formation. So those are the evidences for Snowball Earth episodes. So this is a bit long, but it's a good story, so I hope you enjoy listening to it.